Welcome Calculus BC. This is lesson 1, 2, limits, continuity, intermediate value theorem, and graphing. Let's begin. So just indeterminate limits, a little bit more limit practice. So sometimes you have something that's indeterminate. What does indeterminate mean? Like 0 over 0, sometimes it's infinity over infinity. Those are the common ones where if you just plugged it in, it'd get that. So this first example, this is like 0 on the top and 0 times 1, which is 0 on the bottom. That's indeterminate. Now, we talked about using L'Hopital's rule, and you can absolutely keep doing that. But I'm going to show you how to do it algebraically in this video. So algebraically means like you just cancel things out on the top and bottom. Sometimes you have to factor before, and then you can actually plug in after you cancel things. So take this first example. Since it's already factored at the bottom, I can cancel out these two x's. And so I'm just left with 1 over x plus 1. You plug in the 0. You get 1 over 0 plus 1, or 1s, which is just 1. Great. Now, if you remember L'Hopital's rule, just for funsies, x on top, let's pretend I distributed that, so it's x squared plus x. Now, you derive top and bottom. Top was going to be 1, and it's 2x plus 1 on the bottom. You plug in 0 for those, you would get 1 over 1, which is still 1. So yes, you can do L'Hopital's rule still, but here's how to do it algebraically. This next one, you have to remember something called the difference of squares. So difference of squares is x squared minus a squared, usually it's a letter or something, is factors to x minus a times x plus a. This concept comes up a lot in like algebraic tricks and SATs and any placement tests you do for college. So know this. So this is like a difference of squares I can factor it to. So I can factor this guy out to x minus 2 on top, and its factors to x minus 2 times x plus 2. And you'll notice certain things can cancel the x minus 2, so I'm left with 1 over x plus 2, which you plug in the 2, it's going to be 1 over 2 plus 2, 4 for your answer. Now for number 3, this is actually the difference of cubes. So the formula for difference of cubes is x cubed minus like a cubed. When it's a minus here, it factors to x minus a. I remember same, opposite, plus. And so same sign, and it's x squared, opposite sign, plus, I think it's ax plus, and then a squared. So it's same, opposite, plus. If this was a plus in between, instead of having those signs, it would have been a plus sign here, a minus sign, and a plus right here. Again, sometimes pops up. So anyways, the top factors to an x minus 1 times x squared plus x plus 1 over x minus 1. You'll notice you can cancel out the x minus 1s. So you're left with x squared plus x plus 1. You plug in the 1s. The limit's going to be 1 plus 1 plus 1, which is 3. Or you could have L'Hopital's ruled it. Algebraic techniques. Okay, this one right here. You go, this is actually a difference of squares, and you're going to hate me a little bit. So see this x minus 1, when I see a square root of x minus 1, I'm going to actually convert this. Instead of saying x, I'm going to go square root of x squared. Now it looks like a difference of squares, right? You could do that because square root of 2 squared cancel out. So rewriting that as square root of x minus 1 on top, and the bottom is square root of x minus 1 and square root of x plus 1. So you see what cancels right here, boom and boom. So you're left with 1 over this thing. You plug in the 1s, you get 1 over 1 plus 1, which is 2. So 1/2. All right, this one. If you just plugged in the 2, you get indeterminate form. So you can't factor out, but since it's a right-sided limit, so the plus right there, I'm actually just going to do some test values. Might be one where you just plug in some test values. So I'm going to say x and y. So I'm going to pick, when I say 2 plus, a little bit bigger than 2, so 2.1, 2.5, and let's say 3. So if you plug in those values, what's it going to come out to? If you plugged in a 3, that's the easiest one. So 3 over 3 minus 2 is going to be 3 over 1, which is just 3. Plug in 2.5, you get 2.5 over 2.5 minus 1, so that's like 2.5 over 0.5, which actually reduces to 5. Trust me. And 2.1 over 2.1 minus 2, so 2.1 over 0.1. That's going to be 21. What's actually happening if you get closer and closer to this, you'll see that it's actually going to go up to infinity because the numbers are increasing. So that's usually what's happening in these cases. It's either going to be going up to infinity or down to negative infinity. You got to figure out what's the pattern here. As we get closer to 2, it's getting bigger. So I can trust it's going to infinity. Okay, so this is a good example to do. Okay, discuss the continuity. Is this continuous everywhere? Well, notice that we use this function when x is not 3, and when x equals 3, we use 5. So the question is, if you try to graph this, you would actually get some graph that had a hole at x equals 3. So if that was 3 for your x, there's a hole right here if you try to graph this top one. I don't know what it looks like. So the question is, does this 5 fill in the hole right here? That's what's going on with this. How do you figure that out? Well, plug in 3 for the top one, and we just find the limit for this. Figure out what the limit is for this. And if it's 5, you're going to be good. So limit as x of x squared minus 2x minus 3 over x minus 3. Okay, so you plug in as x approaches 3. Again, you plug in, that doesn't work. So what do you got to do? Well, L'Hopital's rule, or we're going to pretend we can factor. What two factors multiply to negative 3, add to negative 2? Well, that's x minus 3 and x plus 1. Again, you can use your little x thing and do negative 3, negative 2 if you have to do those, or guess and test. So over x minus 3, and you see what cancels out these x minus 3's. So you're left with x plus 1 over 1 as you approach 3, which is going to be 4. Is 4 the same as 5? No. So I'm going to say it's discontinuous at x equals 3. If this 5 and these were both 5, we'd be good. Or if this were both 4, we'd be good. It's continuous everywhere. But this one is actually discontinuous at x equals 3 because they don't match. More limits. Okay, I like this one. So you've seen problems like this, and this appears in the AP test, where like you have this like a here, and they say, if this g of x is a continuous function, find the value of a. So basically, you got to, and this it hands off at 2 right here. You got to figure out at 2 what value of a, if x was 2, what value of a makes these equal. So the top one approach it, and the bottom one have the limit of the same point. So all you do, plug in 2 for a. So I'm going to say, I can even write it like this. G of 2, I'm going to get fancy here, equals, when you plug in 2, you get 3 times 2 squared, so 2 squared is 4, so you get 12 plus a over 2 minus 3, which is going to be negative 1. Okay, I got to make them equal to each other. So it's 12 plus a equals negative 1. What value of a? Subtract 12, you're going to get a equals negative 13. So this is my answer. If you plug in negative 13, you are now continuous. All right, use a calculator to find results. Well, we are going to do that today, folks. Oops, that doesn't work. I didn't mean to do that. Yeah, I meant to do this. So I'm going to play with this calculator on the side. All right, so I can plug this calculator into my T89 right here. So I'm going to graph this equation. This is going to be long to type in. So maybe I'll only do the top one. So I'm going to x cubed minus 3x squared plus x. Oops, x. You just fast forward if you want. Plus 2 divided by x cubed minus 2x squared minus x minus 2 plus 2. Okay, enter. And I typed it in correctly. I'm going to graph this. What does it do? So we're trying to check out as it approaches 1. So where's 1 on my graph? Now I'm zoomed into some weird thing. So let's see. I want to make sure I'm zoomed into standard just so I kind of look like you. So I like to zoom, standard mode. I'm going to hit 6. Okay, so let's see what this looks like. Probably what your calculator is going to look like. So as you're approaching 1, what is it doing? So it's kind of weird, right? So what's happening at 1 is your graph is going up to 1. Actually, I can probably zoom in a little bit. This might be centered right here. See what it does. But it looked like it's going up to infinity on the left-hand side and going down to infinity on the right-hand side. It's exactly what it's doing. So trace, if you try to trace to 1, that's, yeah. And notice here, it's going down forever and then up forever. So what I'm going to say, if I come back to our board here, is we're going to say the limit does not exist in this case because it's approaching two different sides. Now let's change it to the other graph. So changing this one up, is it the same thing? Okay, the difference is, oh, you're approaching 2. Awesome. So let's, okay, I'm going to break that. Let's zoom to standard again, and let's see what it does. Should have paid attention. My fault. Okay, notice here, it looks like it's zooming, it's tracing to something. So I'm actually I'm going to hit trace, hit 2. You can't really see it. So notice here as I go left and right, from the left-hand side, the y value is approaching something as it gets close to 2. And as it go from the other side, it's also approaching that something. I probably have to zoom in a little bit. So we're going to zoom in around that 2. I'm going to say that's the center. Let's see what I can get. Now you can always do L'Hopital's rule and stuff, right? I just have to get values that are close and see what's going on. So I'm going to hit trace. I'm going to trace to 2. I don't see it. I'm approaching, it looks like I'm approaching, it's like it jumps right there between 3.29 and 3.6. So it's probably around, I'm guessing it's something around like a 1/3 or so. Now what's cool is you can also use this table function. I guess we're kind of getting off here. So you can, instead of like tracing like that, I can say, okay, we have to trace around 2, right? So I can start with 2, it's undefined. So I can go to 2.001. A little bigger, and 2.01. Getting a little bigger, and 2.1. So notice how those y values, as you got closer to the 2, it's really getting close to 0.33333. And I bet if I did the same thing, let's see, I'm going to go to just a little bit smaller, so 0.999. And I'm going to go 1.99. And then, oops, I should have done this, 1.9. And you can kind of see these numbers are a little bit smaller than 0.333. So using that tracing, I can actually say my limit is equal to 0.333, repeating, which is the same thing as 1/3. Awesome. Intermediate value theorem. So f is a continuous function. You've done this last year. What is intermediate? Intermediate is like a middle number, right? And so it's like a middle value. So what the intermediate value theorem says, hey, if you got this continuous function f, and it goes from right here on the left to right here on the right, this is all about the y values. If it says the y value is down here like at 1, and the top y value up here is at like 5, it says if it's continuous, then every value between 1 and 5, every y value, is hit at least one time. So somewhere, and that's what it says, value k, so somewhere there's going to be a 3. Maybe a lot. Maybe only be 1, maybe a ton of them. There's going to be at least 1. So as long as they're continuous and one side to the other. It doesn't say anything about x values. It says the y values, everything's going to be hit at least one time. So why is this useful? Well, so let's take a problem like this. Does the intermediate value theorem guarantee a c value? To guarantee, it has to be continuous because it only works for continuous functions. And you have to check the left, and then you have to check the left and right y values. So let's take this function. If you have this function, and we're going to go, these are x values, and see this notation. X is from 0 to 5. Is y going to be an intermediate value? Is 12 going to be an intermediate value? Well, what do we want to do first is I'm going to make a little table. X, y. So x of 0 and 5. When x is 0, and you plug in that, you're going to get a y of 0. When x is 5, you get 5 squared minus 5, which is 20. This is a continuous function. It's a polynomial function. So 0 to 20 says every number between 0 and 20, that means there's some value, so some x value between 0 and 5, where the y is going to be 20. So does the IVT guarantee a c value? Yes. I mean, it's going to be a guarantee that somewhere the y is 20 between 0 and 5. Let's do B. Same thing. I'm going to make a table. So 0 to 3. If you plug in a 0, you're going to get -4 over -2, which is going to be +2. You plug in a 3, you're going to get 9 minus 4, which is 5 over 1, so 5. So this one, it goes from 2 to 5. Is 4 between 2 and 5? Yes. However, so you say, oh, yes, right? Wait a minute. We have to be continuous. Notice this. You're dividing by this. That means you're discontinuous at x equals 2. 2 is between. So we cannot use the intermediate value theorem because it is not continuous. See that? All right. 10. Find the value of c in example 9a. So, okay, great. 12 exists. Where is it? How do we figure that out? Just plug in 12 for this. So I go x squared minus x equals 12. And we can solve this as a quadratic equation. Subtract 12 on both sides. Got to isolate everything, and then we factor that. And again, you can use the x factor thing, but it's going to be x minus 4 times x plus 3, because those multiply to negative 12 add to negative 1. And so that means my two solutions are going to be x equals positive 4 from the left and negative 3 from the right. Which of those values is between that? 4. So c equals 4 is going to be the answer that where f of c is 12. All right. Parent graphs, last thing. So, like, don't have to write these down, but it's good to know some of these. If you don't know some of these, I would write it down. Especially, okay, this one, probably not. This one doesn't appear much. Y equals 2/3 x. But you should know y equals x is a line. This is a parabola. This cubic function looks like this swirly gig thing. This sometimes is neat to know. It looks like a parabola, but gets wider. So when you have an even exponent, you just like a wider parabola. You should know this one. I mean, look at this. It doesn't pop up much. You should know this. Definitely should know this. Probably should know this. This is good. This will come up more than the BC stuff later when we get to more of this circle stuff. And then you should know what sine and cosine function looks like. So parent graphs, and sometimes we can use parent graphs to come up with other graphs. So here's an example. This is a list of adjustments, and you're like, I don't know all these. That's okay. Maybe a few things that are kind of neat to know are, number one, if you put a negative inside in front of a function, it reflects it, so it flips it on the x-axis, so upside down. If you put the negative in here, it flips it across the y-axis, so it flips it vertically, or yeah, all on the y-axis. Now, this one's important. If you do a plus number outside or add or subtract a number, this shifts it up or shifts it down. And if you add or subtract a number inside the function, so with the x, it shifts it left and right. Those are important. This one stretches, so like these are the most important ones you got to know here. This stretches it, so, or squeezes it, and different squeezes. Absolute value, I guess, is important to do. This pops up sometimes. So yeah, this one I haven't seen happen much, so I don't know. But let's see what this looks like. So I got this function over here, like parabola shaped in this line. So if this is our function f of x, when I do these transformations, what happens to this? So as we learned in that last slide, if you do a plus 2 inside, this is going to actually shift it to the left 2. It's like the opposite of the sign, like negative way 2. So instead of that parabola doing that right there, it's actually going to be like off my screen, kind of like that. And then the line's going to go down like that. Bad drawing, but hopefully you get the point. Now, this one, I have a negative f of x and then a plus 2. So you can do the negative part first. So negative f of x is going to flip it. So that's going to make it like upside down like that. So, but plus 2 is going to shift it all up. So this is all going to shift it up 2. So what happens is I got, again, it's a flip. So, but it flips upwards. I'm going to go, and then like that. So it's all flipped first and then shifted up 2. All right. Next one. So 1/2 after the negative x. Now what does that negative x do? A reminder, the negative x reflects across the y-axis. So the y-axis is right here. So it's going to reflect it. That means the u thing is going to go here, and the line is going to be diagonal like this. But since it's 1/2, it kind of squeezes it. So your u is going to look like this. Oops. That. And then the line's going to like do this thing. Like that. So it kind of makes it shrinks it a little bit. Now, absolute value f of 2x. So f of 2x, since that's the inside, let's do that first. 2x as a reminder. So this would be this 6 right here. It's a horizontal squeeze. So if it's going to be squeezed, so you think horizontal squeeze is where if you're doing, hold on. Horizontal squeeze is like you're squeezing it in horizontally like this. So kind of making it skinnier. Got text. So that's going to make this skinnier right here. So it's going to kind of do like this and this. Kind of think of it that way, this and this. But absolute value means that you won't go negative. So it's going to look like this. It's going to look this, but then it's going to go down. But instead of keeping it going down, up, that line, it's going to actually flip back up. So it looks something like that. Like a parabola going down, but then up, come back up because I can't keep going negative. Now this f of absolute value of x, what this does is it says you can never have a negative in here. So it means that everything on the positive side stays the same. But instead of doing the u on the negative side, it just mirrors the positive side. This doesn't happen too much. That's it.